Hello, we're going to look at 5.1, and this is a recursive function. And it says a recursive function is one in which the initial values, use of 0, use of 1, and so on, are given along with a rule, use of n, some function of use of n minus 1, n minus 2, and so on, which explains how the term is obtained from how a term is obtained from the previous terms. So it'll give you a couple and then a rule, and then to get the next one, you have to use those terms, the first terms in the rule, to come up with each other term. Sound good? So to see an example, let's look at example 1, and it says find the first 4 terms of the triangle number sequence given by use of 0 is 0, use of n is equal to n plus use of n minus 1, hence show that use of n is equal to n over 2 times n plus 1. So we need the first of 4 terms. First four terms, we have use of 0, which is equal to 0. That's the first term. Use of 1 would be equal to 1 plus, when we plug it in, use of 0, and when n equals 1, n minus 1 is 0. So it's going to be 1 plus 0, which is 1. And then use of 2 is going to be 2 plus 2 minus 1 is 1, use of 1, and then we go 2 plus 1 is equal to 3, and then use of 3, which is equal to 3 plus use of 2, which is 3 plus 3, which is equal to 6, and so on. So those are the first 4 terms. And next it said show that use of n is equal to n over 2 plus 2, but you can see first term is just 1. This one is equal to 1 plus 2. This is equal to 1 plus 2 plus 3, and so on. So it's just use of n is summing up all the positive integers, right? So that is the common formula known as this, or the way they wrote it, n over 2 is n plus 1. And you can look at chapter 1, has some examples like this, where this is a famous formula by the famous mathematician Gauss, who showed this when he was just a child. So anyways, let's move on to the next example. And so example 2 says find the first 6 terms of the sequence given by use of 0 is 1, use of 1 is 1, and then use of n is 2 times use of n minus 1 plus 3 times use of n minus 2. And then we have to prove it by mathematical induction that use of n is actually equal to this guy right here. So the first term is just the first 6 terms. First 6 terms. First term is use of 0 is 1. Then use of 1 is equal to 1. Then use of 2 is going to be 2 times. When I plug it in there, it's going to be use of 2 minus 1 is use of 1 plus 3 times use of 0. And it's going to be 2 times use of 1 is 1 plus 3 times 1. And then we're going to get, this is going to come out to 5, right? 3 times 1 is 3, 2 times 1, add them together, we get 5. Use of 3, this would be the 4th term. And then 2 times use of 2 plus 3 times use of 1, which is 2 times use of 2 is 5, and use of 1 is 1, so that's 10 plus 3, which is 13. And then use of 4 is going to be 2 times use of 3 plus 3 times use of 2. 2 times use of 3 is 13, and then 3 times use of 2, which is 5, and this is going to be 26 plus 15 is going to be equal to 41. And then use of 5, which is the 6th term, 2 times use of 4 plus 3 times use of 3, which is 2 times use of 4 is 41, and 3 times use of 3, which is 13, and I'm going to get 82 plus 82 plus 39, and it's going to be 121, and there you go. So, and that's the first 6 terms of the sequence. Good. Now the next thing you want us to do is prove this by using mathematical induction. So we're going to prove a recursive sequence using mathematical induction. So first thing to notice about this recursive sequence actually has two first terms. So I'm going to have to show that piece of 0 using this. So I'll go use of 0 is equal to 3 of 0 plus negative 1 of 0 all over 2. That's going to be 1 plus 1, which is 2 over 2, which is 1. So that first term is good. But we also have another first term in the sequence, which is use of 1. And I'll go 3 of 1 plus a negative 1 to the 1 over 2. Well, that's going to be 3 minus 1 over 2, which is also going to be 1. So therefore, a piece of 0 and piece of 1 is true. So we did the first part of the proof. Now, piece of k, I have to assume that use of k is equal to 3k plus negative 1 to the k all over 2 is true. So I want to use this assumption to prove that every other term after that is also true. So the last step is to show piece of k plus 1. I need to show that use of k plus 1 is equal to 3 of k plus 1 plus negative 1 to the k plus 1 all over 2. I need to show that this guy equals that. So let's go through it. What is use of k plus 1 equal to, right? Well, I need to show this. I can't use this one. I need to use my recursive sequence right here, right? So that's going to be equal to 2. When I put k plus 1 into n minus 1, I'm just going to get use of k. When I put k sub plus 1 in here, I'm going to get 3 times use of k minus 1. Good. Now I can use my assumption that I have right here, right? So I can use this guy right here to help me out. So I'm going to move up so I can get a little more space. Right there. So, and then I'll get 2 times, when I plug this guy in, I'm going to get 3k plus a negative 1k all over 2 plus 3 times, when I put k minus 1 in here, I'm going to get 3k minus 1 plus a negative 1 to the k minus 1 all over 2. Good. Now I'm trying to make it look like this guy right here. So I notice that there's a 2 in the bottom and I need a 2 here, so I have like terms. So I'm going to go 2 times 3k plus 2 times negative 1 to the k plus, if I take that 3 times that, I'm just going to get 3 to the k, and then I'm going to get plus a 3 times a negative 1 to the k minus 1 all over 2. Now what's good is here, these are like terms, right? 2 plus 1 is 3, so I'm going to end up with 3k plus 1. So that's good. These are not quite like terms, right? But I can work with this guy right over here, right? So what is this guy equal to? Well, if I take out the negative 1, I end up with negative 1 to the k, right? To the negative 1. So I'm going to end up with a negative. This ends up being a negative, just a negative 1 of a negative 1 to the kth power, right? So what am I going to end up with? 2 negative 1 to the k plus, I added those together, and then I'm going to get 3 times, it's going to be a negative 3 actually, to the negative 1 times k, right? Good. And then all over 2. Good. So what do I end up with? 3k plus 1 minus negative 1 to the k all over 2, right? Well, if I consider this, what is this equal to? 3 to the k plus 1. This could be plus a negative 1 times a negative 1 to the k all over 2. That has a power of 1. Sorry, went off. Finally went off. So I'll just re-go forward again. I changed 2 minus 3 is -1. And then this became, I can write it like this to the first power, and then I end up with 3k plus 1 to plus a -1 to the k plus 1 all over 2. And this guy is what I wanted to show right here. And then I can say, therefore, piece of 1 and, I should say piece of 0, piece of 1 is true. And piece of k is true implies that piece of k plus 1 is also true. Then the statement is true for all n. And there we go. And that's the end of the proof. Thanks, guys.